Hello everyone, my name is Yi Xiang. I'm a researcher from the University of New South Wales. The topic of my paper is about community search over large heterogeneous information networks. Conceptually, a heterogeneous information network is a network with multiple types of vertices and multiple types of edges. Typical examples are DBLP network, Twitter, Foursquare, and knowledge bases like Yago and DBpedia. A fundamental research topic in HNs is to find the network communities, which can be used in many real applications, such as recommendation, event organization, and network analysis. In the literature, to find the network communities, there are two groups of works. The first group is called community detection, which aims to find all the community from a graph in an offline manner. However, these methods cannot answer personalized online community queries. To address this issue, the community search methods are developed, which aims to find a community containing a specific query vertex. So compared to the CD methods, CS methods are more personalized, efficient, and scalable. We summarize all the existing works in this table. As we can see, none of the previous works has studied the CS over HN, so our work is the first one to study CS over HN. Let's see a motivating example. This is an HN of the DBLP network. There are 6 authors, 6 papers, 1 venue, and 2 research topics. Then a natural question is how to find a community of researchers. Note that in this paper, we mainly focus on finding community of vertices with the same type. Usually, a community often needs to satisfy 2 criteria. The first one is the connectivity. That means each vertex is connected to the others in the community. To do this, we use a metapath to establish the relationship between two vertices of the same type. Here are 2 metapaths. The first one describes that 2 authors with the co-authorship. The second one describes that 2 authors who work on the same research topic. The second criteria is the engagement, which means that each one is well engaged in the community. To achieve this, we use the Keiko model, which requires that each vertex is connected to at least k other vertices in the community. Based on the above discussions, we propose the basic KPK model, which corresponds to a set of vertices such that each vertex is linked to at least k others while k instance of P. Then the HN can be induced to a homogeneous graph. For example, given a metapath APA, then we can build a homogeneous graph of authors like this. 2 authors are connected by age if they are linked by a metapath in the HN. However, this model has the issue of weak engagement. For example, we can see that A5 is connected to 3 authors while 3 metapaths. However, these 3 metapaths share the same age between A5 and P5. This means that if this age is removed or wrongly collected, then A5 will be isolated from the community. This issue will be even more serious for longer metapaths. To address this issue, we propose the age-disjoint KPK model and the vertex-disjoint KPK model, which correspond to a set of vertices such that each vertex is linked to at least k other vertices, while k age-disjoint or k vertex-disjoint paths of P. The 3 kinds of KPKs are used to model the network communities in the HN. The specific problem definition is as follows. Given an HN, a query vertex, a metapath, and an integer k, and a specific KPK model, then the goal is to find the set of vertices in the corresponding KPK containing the query vertex. Let's see an example. Suppose the query vertex is A1, and the metapath is APA, and k equals to 3. If we use the basic KPK, then we will find a community of 5 authors. However, if we use the age-disjoint KPK, then we will find a community of 4 authors. Please notice that A5 is excluded from the community. This is because A5 has only 1 age-disjoint path to others, while for other 4 researchers, each of them has 3 age-disjoint paths to others. So you can see that the community of age-disjoint KPK is more cohesive than that of the basic KPK. To solve this problem, we propose efficient online algorithms Specifically for each core model, we develop a baseline algorithm and an advanced algorithm. You can see that there is a trade-off between the cohesiveness and efficiency. Generally, a more cohesive core takes higher computational cost. We also develop efficient index-based algorithms. We build an index which is able to index all the cores for a given set of metapasses. Based on the indexes, the query can be completed in the optimal time cost. Next, we focus on discussing our online query algorithms. For the basic KP core model, we propose a baseline algorithm which works as follows. We first build an induced homogeneous graph and then compute the connected K-core from the homogeneous graph as the community. For example, given a metapath APA, then we build a homogeneous graph like this, and then the connected K-core in this homogeneous graph can be regarded as a community. However, this homogeneous graph is often very dense, so the computation is very costly. To improve the efficiency, we propose an advanced algorithm which does not need to build an induced homogeneous graph. Instead, for each vertex, we only find up to k metapasses linked to it, and then iteratively remove vertices that are without k metapasses. Obviously, this algorithm runs much faster. The computation of edge-disjoint KP core is more challenging because it cannot be computed from the homogeneous graph, so we have to compute it from the HN directly. The key step of computing the edge-disjoint KP core is to count the number of these disjoint passes. We propose both exact and approximate algorithms. For exact algorithm, we build a flow network and use the maximum flow algorithm to find the maximum number of edge-disjoint passes. For approximate algorithms, we work in the greedy manner by iteratively finding a path and remove its edge from the graph until there is no other path. So you can see that the grid is much faster than exact. Here is example. Suppose the map path is APA. For exact algorithm, we will build a flow network like this, and then we will find that there are 3 edge-disjoint passes. Well, if we use the greedy algorithm, we may find only 2 such passes. Based on the counting algorithms, we propose a baseline algorithm for computing the edge-disjoint KP core. It iteratively executes the following steps for each vertex. First, we count the approximated number of edge-disjoint metapaths by gradient. Second, if the approximated number is less than k, then we run the exact algorithm. Finally, if the exact number is still less than k, then we remove it. So you can see that this algorithm removes vertex one by one, so it may be slow if there are too many vertices that need to be removed. To improve the efficiency, we propose an advanced algorithm which works in a batch manner. Specifically, we first find up to k edge-disjoint metapaths for each vertex by gradient. Then we iteratively execute the following steps for a batch of vertices. For vertices with out k edge-disjoint metapaths, then we run exact. After that, we remove a batch of vertices without k edge-disjoint passes. For vertex-disjoint KP core, the computation is similar, except that we need to slightly update the flow network. We have performed experiments on 5 very large HNs. The results show that for online query algorithms, our advanced algorithms are over 1 order of magnitude faster than the baseline algorithms. Also, our index-based algorithms are much faster than the online algorithms. We have performed 2 case studies on the DPLP network. For the first one, we let the query vertex be Professor Schmidt and use the metapath APA. The communities of the basic KP core and the edge-disjoint KP core are listed as follows. We can see that they share the same set of 6 authors, but the first one has 13 additional authors. After a deep investigation, we found that these 13 authors are actually Professor Lin's former students who published only 1 or 2 papers with Professor Lin, while other 6 authors collaborate with each other intensively. So you can see that the community of edge-disjoint KP core model is more cohesive. For the second one, we try to find the community of sigma conference. We can see that edge-disjoint KP core model is able to find the top 6 conference in database area, while the basic KP core model may find a conference in other areas like security. So you can see that the community of the edge-disjoint KP core model is more meaningful. That's all. Thank you.